This is a supercut of the videos for MCC in VS Code, focusing on the MCC Melody content library. We'll give the short highlights of each video, but welcome to the series to watch these at a normal pace. In this video, we're going to be looking for example projects in Discover. So first we filter on the content type for MCC Melody. Since we want to use the I2C bus, we filter on I2C under peripherals. Under device family, AVR will find all the new AVR families, pointing out a useful MPLAB harmony video with Discover where we show how to modify a project from one board to another. The principles apply here too. Filtering on Q under device family shows all the new PIC18F families. We then click on advanced mode and show how one can use AND and ORs in the filters. We find an interesting project which finds all the clients on an I2C bus. We see what it looks like when running and expect 10 devices on the Curiosity Nano Explorer. We download, then import by simply opening a folder. We then get prompted to open the project and a build starts automatically. So we can immediately run, debug stops on entry, and we can open the data visualizer and run the project and get the same result, verifying we do get 10 devices. Next, we find the user guide of the Curiosity Nano Explorer, showing off some pretty cool navigation features in this document. In the second video, we create a new MCC Melody project from scratch, implementing a 100 millisecond timer with LED and debug IO. We start with an overview of the basic MPLAB commands, Ctrl-Shift-P to find all commands, everything really starting with MPLAB and then MCC or MPLAB data visualizer or MPLAB create new project, which we use. We happen to be using a PIC18F Q43. We select a compiler, we open MCC and select the defaults, and our project opens. And then add a timer example. We select one of the two examples, then show the spec behind the example components, the MCC Melody design patterns for control flow. We select an interrupts with callbacks implementation and a LED with debug IO visualization. Going through the configuration steps, we show that there's context help available. So we add a timer, select a MPLAB. Now, in order to meet the required 100 milliseconds, we need to change the clock associated with the peripheral library. Then we can check off the steps we've completed. Go to our kit window to find our schematics so that we can configure our LED and debug IO. We configure those pins. Once we generate code, we can go into our generated example code, copy and paste into main, handle any to-dos, in this case just selecting our timer number, control click to navigate and go into files. And now we build the project, run and debug, we run, now we open the MPLAB data visualizer, add to a plot, and use the new scope mode to verify the timer period that we configured. As an intro to multiple configurations, we create the simplest possible MCC project, creating a project and then creating an MCC configuration inside that project. Next, we show MCC.VS Code, the connection between the MCC config and the MPLAB configuration. The MPLAB configuration is the project.json, and we notice that initially the file set is empty until we generate code. Then the files are populated. At this point, we can build the project with no errors. We close the folder and start again, now creating a standalone MCC configuration, naming it I2C proximity sensor, since that is the use case we'll look at. We create a folder which will become our workspace. We add the I2C host example component and view some of what these examples do. The various proximity sensor visualizations are what we will implement. Starting with the polled implementation and the printf visualization, we just implement a pseudo configuration, just adding the relevant components but not configuring them fully. That gets done in the last videos. The pseudo configuration is enough to talk about the concepts of multiple configurations in MCC. Checking the MCC.VS Code, there's no associated project because we don't have one yet. So we create an MPLAB project, saving it in the workspace level folder we created. We then run the configure associated project command to link the two. The default file set is empty until we generate code. The MCC configuration is compiled, and next we create a new configuration. This time I2C proximity sensor callbacks and data streamer visualization. Before creating an MCC configuration, we first create an MPLAB project configuration, opening the GUI, naming our default configuration, called printf, and then creating a new one, callbacks data streamer. We find the file set and delete all the files. These will be replaced when we complete the new configuration and generate code. Completing our new pseudo configuration, we connect the new MCC configuration to the MPLAB project configuration of callbacks data streamer. We can now generate code, and we can see that the project builds. Continuing from where we left off, we view our MCC configurations in File Explorer, copying and pasting the data streamer configuration to DV runtime, then going into the folder and renaming the MC3 file DV runtime as well. Back in VS Code, we add this folder to our workspace, noticing that the MCC.VS Code still connects it to the data streamer config. We remove that and now open MCC on the DV runtime configuration. Since this was copied from the data streamer configuration, that is the state of the MCC configuration when we open it, so we can modify it from here. We add the DV runtime and remove the data streamer libraries. Then select DV runtime dependencies. Opening the project.json, we create a new DV runtime MPLAB project configuration. Now we use MPLAB MCC configure associated project to link our MCC configuration to this new MPLAB project configuration. This time we leave the existing file set and generate code, noticing how the new files are added at the bottom. So we remove the files associated with the data streamer and are left just with the DV runtime source files in our file set. Changing the project.json triggers a build, which compiles successfully. We now use File, Save Workspace As, and save our workspace in our workspace folder. This contains an MPLAB project and 3 pseudo MCC configurations, which in the next 3 videos are built out and verified on hardware. Starting with the polled printf, we complete the configuration, copy and paste example code, run the code, open the data visualizer, and here we can see the polled printf application working as expected. Similarly, when the callbacks data streamer configuration is done and the code updated, we can open the data visualizer and navigate to the .ds file, which contains the variables that the data visualizer should expect. From top to bottom, in blue we have the proximity sensor reading, in green a frame count, in yellow toggling a debug IO each time we send a frame, and at the bottom the raw hex values of the frames we are sending from the microcontroller to the data streamer. Once the DV runtime configuration is done and the example code updated, we open the DV runtime project configuration, naming the ELF file so that we can easily find it. Also quickly noting its output directory. In the data visualizer, we open a new DVRT session. Once we've loaded our ELF file, we're able to search for volatile and static variables which are in our code, and also plot their values at runtime. This makes the DVRT an extremely powerful runtime debugging tool, so you don't have to specifically keep updating the frame of variables that you might be interested in. So that was a very quick overview. Welcome to the series to view these videos at a normal pace.